Now we will apply the Empath Law to calculate the magnetic field in a system that very useful in practice, that is the magnetic field of a solenoid. The solenoid is the conducting wire that is curved into the shape of the coil. It's much like the coil spring, okay, like this. And when we pass a current through the coil to the solenoid, we know that this current will produce the magnetic field, okay. And we know that the magnetic field from the current solenoid is very similar to the magnetic field from the bar magnet, okay. So in practice, we can use this solenoid when we need the source of the magnetic field, and this magnetic field will be very similar to that of the bar magnet. So we also call the solenoid as a electromagnet. It means that we can produce the magnetic field that very similar to that from the magnet by passing the electric current into the solenoid. So the solenoid is a electromagnet, the magnet that is created from the electric field. Okay. This is one of the practical purpose of the solenoid, that we use it as an electromagnet. The solenoid also have many applications. We use this configuration of the conducting wire as a solenoid in the alternating current circuit that we will study soon. And we also use the solenoid to produce the strong magnet when we put some material that we call it the ferromagnetic material inside the solenoid. Okay. For example, if we put an iron bar inside the solenoid like this, okay, the magnetic field from the solenoid will induce this iron bar to be the very strong magnet. So we can use this configuration to produce the very strong magnet that have the many applications in engineering, in physics, in medicine. Okay, so solenoid is very useful. Here we will discuss the field, the magnetic field that produced by the solenoid, especially the magnetic field that produced inside the solenoid. How can we calculate that magnetic field? And we can use the Empath Law in our calculation. Here we will discuss only what we call the ideal solenoid. Okay. What is the ideal solenoid? The ideal solenoid is the solenoid that is very long. And when we say that the solenoid is very long, it means that the length of the solenoid is much larger than the diameter of the solenoid. Okay, like in this figure, if the total length of the solenoid is much larger than the diameter of the solenoid, we call it an ideal solenoid. Okay, and we will calculate the magnetic field with near the middle of the solenoid. We will not calculate the magnetic field at these two ends of the solenoid. The magnetic field at these two poles can be quite complicated, and we will not discuss here. If you need more advanced mathematical tool to discuss the magnetic field at these 2 points. But the magnetic field near the middle, if the solenoid is very long, can be analyzed quite easily. Okay, and how can we do that? We can use the Empath Law that we have discussed so far to analyze the magnetic field close to the middle of the solenoid, of the ideal solenoid. We will divide our discussion into T parts. Okay, part 1, part 2, and part T. Let's start from the part T first. Okay, we want to calculate not calculate, but we will apply the Empath Law to this loop. This is a solenoid, and we have the Y that curve as a coil spring. The current point out of the plane at this point and point into the plane at this point. Okay, and if we create a surface that has the boundary as a loop number 3 like this, we can see that the net current that passes this surface is 0, right? Because we have the current that pass out from the plane and have the current that pass into the plane like this, and we have it in a pair. So this current and this current will cancel each other. I mean that the current that pass out, we have the current that pass out and pass in. So the net current that pass to the surface is 0. So we have I is 0. And when we apply the Empath Law to this loop, when we apply the Empath Law to this loop, we have the Empath Law. The integral of the closed loop is equal to mu 0 I. But for the loop number 3, I is equal to 0. So we have that the integral of B dot ds is equal to 0. Right. In this situation, we have that the integral of B dot ds is 0. The possible way to get the 0 integration here is that B is 0. Because we know that ds is not 0, we have the loop number 3 here. So we have the ds. ds is a displacement vector. Okay. So we must have the ds around the loop. So the ds will not equal to 0. So it means that it's possible that B is 0 everywhere on the loop, or B is perpendicular to the ds everywhere on the loop. If B perpendicular to ds, it means that B dot ds is 0, because cos of pi over 2 is 0, right? But we know that from experiment, we know that the solenoid will produce the magnetic field. So it means that B cannot be 0. So we have to choose the second choice. That is, we must have that B is perpendicular to ds everywhere on the loop number 3. Okay. Now you can see that if we look at the loop number 3, outside the solenoid, we can have the ds, the vector ds, in 2 directions. That is, at this direction and at this direction. So how can we have the B that perpendicular to ds everywhere? It means that B must be perpendicular to ds on this direction and also on this direction. So what we have is that B must be point into the screen or point out of the screen, right? Because these two ds form the plane on the screen. Okay, so outside the solenoid, the magnetic field must point into the screen or out of the screen. But inside the solenoid, we also have the choice that the magnetic field can point along the axis of the solenoid, because you can see that ds here point in this direction, and if B point along this direction, we can have that B is perpendicular to ds. Okay, and we will show soon that inside the solenoid B will point in this direction, but outside the solenoid B must point into the plane or out of the plane. Okay, so when we apply the Empath Law to loop number 3, we have the result that B must perpendicular to ds. Outside the solenoid, B must point in or point out of the plane or of the screen. Inside the solenoid, B can also point along the axis of the solenoid. Okay. Now, let's go to loop number 1. This is the loop number 1. In the loop number 1, we create the circle, the circular surface that is perpendicular to the axis of the solenoid. Okay, and from this surface, we can analyze the magnetic field outside the solenoid. When we look at the solenoid in this figure, it seems that the current in this side point out of the screen, and the current on this side point into the screen. But actually, the current is not point perpendicular to the screen, not perpendicular outside of the screen and not perpendicular into the screen, but it will make a little angle along the axis, right? Remember that the solenoid is a wire that we curve it as a coil. So it means that when you pass the current inside the solenoid, you must have the current that go from one end to another end like this, right? The current will go in the helical path from one end to another end. So it means that if you create the circular loop, that the circular loop that is the boundary of a circle. The plane of this circle and the plane of this circle is perpendicular to the axis of the solenoid. We must have the current that pass to this surface. And from Empath Law, it means that we must have the magnetic field around the solenoid. Okay, we must have the magnetic field around the solenoid. And also, from the right-hand loop, we know that the magnetic field will point somewhat along this circular path. Okay, and from when we the analysis of loop number 3, we say that outside the solenoid, we must have the magnetic field that point perpendicular to the plane of this of the screen or of this paper. So it means that if the net current in the solenoid point upward like this, if you put your thumb in the direction of I, you must have that the magnetic field will point in this direction. Okay, It means that on the left, the magnetic field will point out of the plane. And on the right, the magnetic field will point into the plane like this and form a circular path that is perpendicular to the axis of the solenoid. Okay, we call this the weak field, which we will explain shortly. That's why we call it the weak field. Anyway, the configuration here, we don't have the symmetry in the configuration here, because we can see that the current can pass through any point on the surface. It depends on where the surface is. Okay, so we cannot use the concept like when we calculate the magnetic field from the state y, the current that pass through the state y in this case. So we know that we must have the magnetic field, but to calculate the value of the magnetic field is quite complicated. So we will not calculate the magnetic field outside the solenoid here, but we know that it is a weak field. Why we call it a weak field, we will see when we analyze the loop number 2. Okay, so we know the outside of the solenoid we have the magnetic field that curl or circulate around the solenoid. Now let's go inside the solenoid. To analyze the magnetic field inside the solenoid, we will analyze the loop number 2. Okay, now we create the loop that pass into the solenoid. We have the path that is inside the solenoid. Okay. In this case, we must have we know that we must have the magnetic field inside the solenoid, right? From experiment we know that there is a magnetic field inside the solenoid. So it means that if we look at the loop number 2, okay, this is the loop number 2, we cannot have that the integral b dot ds is 0 everywhere. Okay, because when we look at the loop number 2, we have the current that pass through this loop, pass through the surface that has this loop as a boundary, right? So we know that the right hand side of the Empath Law is not equal to 0. So we know that this term is not 0. So this term is not 0. So it means that b cannot be 0. But from the analysis of loop number 3, we know that b along this path must be 0. Okay, and b along this path must be 0. Okay, so it means that we only have the magnetic field here inside the solenoid. So the integral of b ds, we can say that the integral of b ds here is just the integral of b ds along the path number 1, which is this path. Okay, which is this path. Now, how can we evaluate this? We can now use the symmetry to analyze this calculation. The symmetry here means that we know that the magnetic field, okay, the magnetic field along this path must be the same everywhere, because when we look if we are at each point on the path, the segment number 1 of this part of the path number 2, when we look to the current that come from the solenoid, we will see the same picture everywhere. Remember that we are interested in the region near the middle of the very long solenoid. It's not at the near the top or the near the end of the solenoid. So it means that if you look at the current, you must see the same picture everywhere. So it means that the magnetic field on this segment number 1 must be the same everywhere on this path, right? And also we know that the magnetic field must perpendicular to this ds, and the magnetic field that perpendicular to this ds, we have two choices. That is, the magnetic field may point in or point out of the plane, okay, or perpendicular to the axis of the coil, or the magnetic field may point in this direction. Okay, the magnetic field may point in this direction. Okay. Or maybe it's possible to point in this direction also, but we will show that which one is the correct one. Okay. Now you can see that if we choose this situation and we do the integration of b dot ds on the segment number 1, we will have that b is perpendicular to ds, because in this part ds point in this direction. Okay, let me change a little bit the direction of ds. So far when we do the calculation in the loop number 3, we say that the ds point in this direction. In fact, we can have the ds point maybe counterclockwise like this, or clockwise. It's the same. We will get the same result. Okay, so when we look at the loop number 2, this loop, okay, we have discussed it before when we discussed the Empath Law. That is, the direction of ds must follow the right hand rule. When we look at the loop number 3, you can see that the current, we have the current that also point out and point in to the plane. So there is no net current, and when there is no net current, we cannot specify the position of our thumb to use the right hand rule. So the ds can point in any direction, maybe this direction or on the opposite direction. But for the loop number 2, you can see that for the loop number 2, only the current here that pass to this loop, and the current point into the surface, right? So it means that follow the right hand rule, we must have the ds in the loop number 2 that point in this direction, right? If you point your thumb into the plane of the screen, okay, which is the same direction of the current here, and you curl your forefinger will curl in this direction. The clockwise direction like this. Okay. Now we have the ds on the loop number 2 point in the clockwise direction like this. Okay, now you can see that when we know that ds must point in this direction, if we choose the situation that b point in this direction, which is perpendicular to the ds here, but it also perpendicular to the ds here. Okay, so it means that if b inside inside the solenoid point in this direction, we will have that the integral of b ds on this segment equal to 0, because we will have that b perpendicular to ds in this segment, and b ds is 0, which is impossible, right? Because we know that on the loop number 2 we must have on the loop number 2 we have the current that passing through the surface that have the loop number 2 as a boundary. So the term mu 0 I is not 0. Okay. So the magnetic field cannot point in this direction. So this is impossible. The possible way is that we must have this or this. Okay. Now, in this case, we have that the current point into the plane like this. So we have that b point into we must point along the axis of the solenoid, right? And you can see that we have two choices, that b point in this direction and b point in this direction. But you can see that if b point in this direction, b dot ds will have the negative value. But if we define that the current if the current point into the plane of the screen like this, from the right hand rule ds must point clockwise, and if we say that this is a positive direction, so it means that this integral, if we say that I point in is a positive direction for this loop, okay, so it means that this mu I, okay, I will explain what the meaning of n soon, but this mu I is positive, L is the length is positive, so it means that b dot ds must be positive, and b dot ds must be positive if b point along this direction. Okay, so it means that this is impossible. So we have that b inside the solenoid must point in this direction. Okay, and we also know that the b must be equal or identical every point on this part, on this section of the loop number 2. So when we do the integral here, we know that b is, here we know that b is parallel to ds, and also we have that b is constant. So we have that b dot ds, this term is equal to b ds, and b is a constant. We can take this b outside the integral, and we have this as the integral of b ds along the segment number 1, and the integral of ds along the segment number 1 is nothing more than the length of this segment, which is equal to L if we define it as L. So we have that this b integral of b dot ds is bl. Okay, so we have this bl. Now, what is this n? N is the number of the current that passing to this surface. Okay, so if we count the number of the current or the number of the Y, okay, if we count the number of the Y that passing this loop, this is N. Okay, for example, in this figure we have that this N is equal to 1, 2, 3, 4, 5, 6, 7. Okay, so if we have 7 Y that pass to this surface and each Y carry the current I, so the total current that pass to this surface is Ni. Okay, so we have that BL equal to mu Ni. If we rearrange this to get B, which equal to mu 0 N over Li, we call this N over L is the density, the Y density, or the Y density or the coil density, which is the number of the Y per unit length, N over L, and we use the small n. So we have that B is equal to mu 0 Ni. Okay. Now we will explain that why we call this a weak field. When we look at this relation, we have that integral B dot ds is equal to mu 0 I. Even we will not calculate B here, but we know that this B is proportional to this N, right? But when you see the field inside the coil, you can see that B is proportional to mu Ni. And in the practice, in practical, N can be very large. Like we can have the N is 1,000 Y per like a centimeter, or 1,000 maybe too much. But we can have N is equal to the 100 per centimeter. So if we compare the current I here, I is equal because the I is current in each Y. But in this case, we have this N times I. So the magnetic field here is must be very large compared to the magnetic field outside the solenoid. Okay, so that is the reason that why we call this the weak field, because the magnetic field outside the solenoid will be weak if compared to the magnetic field inside the solenoid. Okay. You may wonder that, okay, when we analyze the magnetic field here, we use the current on the right side. Can we use the current on the left side? You can do that very quite simple by doing the same process that if we form the loop number 2. Now, instead of the loop that form on the right side, we form the loop on the left side. Okay, and again, since the current point out of the plane from the right hand loop, we must have that the ds must point in this direction. Okay, it is interesting that when you look at the ds inside the solenoid on both loop, this loop and this loop, the ds here and here point in the same direction, but outside the solenoid, outside the solenoid here it point in the same direction also, but in this part it point in the opposite direction. But that is no effect. The main thing, the main effect is here, that is the ds here point in the same direction, which means that if we know that there is a magnetic field here, the magnetic field must point in this direction, because in this loop we define the current the positive current in the direction that point out of the plane. So to get this integral to be positive, it means that B dot ds must be positive in this segment of this loop, and with the same reason we must have that the magnetic field must point in this direction. Okay, so you can use the loop that on the right side of the solenoid or on the left side of the solenoid, and will give the same result. So now we have the formula for the magnetic field inside the solenoid. B is equal to mu 0 Ni, and we will use this formula later to calculate some property of magnetic property of the solenoid.